Let me remind you of the session last time. Defined you some A1 invariant motivic contract, which was given by some explicit formula, what was essentially the initial A1 invariant CDH sheaf on schemes which extends classical motivic formal. Looks like a simple universal definition. It turned out to have some subtle reasons to enjoy the sort of properties that we wanted, namely satisfy the perfected bundle formula. That was core input into proving that this homology was therefore represented by the subtle motivic integers in the motivic homotopy category, given by taking some slice of the unit, and the Bayesian translation bound isomorphism held that in degrees below the weight, this motivic homology with finite coefficients would just be the same as the tau homology. We also discussed symptomic cohomology with T-complete cohomology theory, and we had a comparison statement that the A1 invariant motivic cohomology mod P can be produced from the symptomic cohomology. I give the statement mod P, it could work modulo any power of P, by first discarding the stuff that we always need to discard in degrees above the weight, and then forcing it to be an A1 invariant CDH sheaf. So, for example, in just the case of FT schemes, how does this formula look? Well, then the symptomic cohomology is described, at least on smooth schemes, by the cohomology of this explicit sheaf of abelian groups, this omega j log, which I recall is the subsheaf of omega j, that's the sheaf of differential forms, that's generated by log forms. Things that look like df1 over f1 wedged through dfj over fj. And so I say recall or don't, because you're not going to need to know this formula. So if you sort of fall asleep at some point and you're waking up, I want to present, in fact, in the first half of this talk, a key argument that is used throughout the development of this theory, which will be phrased in terms of this object, but you don't need to know what this is. It's some sheaf whose cohomology we care about, but there's the formula for it. And so specializing this formula in the case of FP schemes tells you that the A1 invariant mod P on FP schemes is given by taking the cohomology, the CDH cohomology of the sheaf, and forcing it to be A1 invariant. And I mentioned to you several times, and there were some questions about this too, that the A1 localization kind of seems to be redundant, because we knew that if we applied our recipe to K theory, then to output KH, the A1 localization was actually not needed. I could have stopped just after the CDH simplification. And so I want to prove one manifestation of this to illustrate the argument. So in fact, the A1 localization is unnecessary. Everything is now living or wild on schemes of characteristics.
I'm so sorry to interrupt, but just, and you'll probably get to this, but just to orient myself, we're kind of trying to think of K theory as being the homotopic part and the TC part, and here.
So the moment there's no spike.
Okay.
The moment there's no TC part.
Okay, right. So
the moment there's no
A1.
TC part.
Okay,
Yeah.
right.
It's not
I was just
the
wondering.
moment everything is still on the only
somehow.
concept. No.
Okay, great.
Because something very similar will appear in the TC part.
Okay.
Absolutely.
Thank you. Thank you.
Yeah. But the moment everything is still on the A1 variant side, on the KH side of the story. Move down. Okay.
Also, one more question, sir. As we still haven't established that this commodity satisfies projective bundle.
No, you're right. Give me 3 minutes. Okay. So I want to prove this theorem. It illustrates an important technique. which is the SSSS technique. To be explained.
Okay.
So we currently have various cohomology theories floating around. Like motivic, symptomic, Ital, and so on. And we have things that could be called non-commutative invariants or localizing invariants in the sense that they're defined at the categorical level. So these are things like K-theory, THH, TC, homotopy invariant K-theory, and so on. And we have various statements to the form that when we plug in a scheme, the objects here have filtrations whose graded pieces are some cohomology terms. And so we have various spectral sequences like this, and through these spectral sequences, we get some obvious flow of information, let me say. Right, if I know that K-theory can be broken up into pieces which are some cohomology theory, and I know everything about the cohomology theory, then I know everything about K-theory. This is not the obvious flow of information, but I claim that we can sometimes go backward. Because sometimes spectral sequences are small. And so sometimes, if you understand what's on the right-hand side of the diagram, you understand what's on the left-hand side of the diagram. And so this technique is also what's used to prove the projective bundle formula for the A1 invariant motivic cohomology. Because we know that the A1 invariant motivic cohomology refines A1 invariant K-theory, and now A1 invariant K-theory has projective bundle formula. In fact, any localized invariant automatically has projective bundle formula. And so the idea is to try to argue backwards. And I want to illustrate that argument in the simplest possible case, which is proving A1 invariance of this.
Could you just say, is KH defined on a level of categories?
It's defined at least for Z-linear categories, yes.
Ah, okay.
We carry out Slytherin construction at the categorical level. Yeah, so at least for Z-linear categories.
Okay.
And in particular, it automatically has projective bundle form. Okay, so here's a sketch of how the proof goes of this A1 invariance claim. And you'll see how this argument. So it's enough to check the claim in the case of evaluation limits. Let me give this map a name, EJ. I'm going to check that two CDHQs are the same. So I can reduce to the case of the local rings. We know those evaluation rings. So it's enough to check that this is an equivalence for all Ancelian evaluation rings. V, okay, again, everything is over FP for a bit. And I can even assume that this valuation ring has dimension at most 1. So as I say, I reduce the valuation rings by this passage to source, to the local rings. And then you use what's called an excision argument. So valuation rings The prime ideals in evaluation ring are particularly simple. It's a linearly ordered chain of ideals. And what you can do is you can pick one of these, and somehow everything that you want to know about the evaluation ring is either given by the primes below it or the primes above it. That is to say, it's either given by the valuation ring mod P, that recalls all the primes above it, or it's given by the valuation ring localized at P, which remembers all the primes below it. So you can carry out some argument like this to glue the cohomology that you want for V from V localized at P and V mod P. And these are both valuation rings, again, of smaller dimension. You do some inductive process like this to then get down to the case of a valuation ring of dimension 1, or maybe even a field. So I've got down to checking my assertion on Hessian valuation rings.
I'm so sorry, could you just say that one more time, just like the whole,
I can say the whole thing one more time.
Yes.
I take my valuation ring.
yes,
So general property of valuation rings is that prime ideals, they just fit in a chain. There's not some complicated graph of prime ideals, there's just one long chain of prime ideals. I pick one somewhere in the middle. Now, if I localize my valuation ring at this prime ideal, I still see the prime ideals that were contained in my original one. And if I take my valuation ring mod the prime ideals, I still see the prime ideals that were above it in the chain. And this V localized at P and V mod P, these are still valuation rings, which now have fewer prime ideals, but they have smaller dimension than the original one. And there's some gluing argument, which is called excision, that I'm not explaining in detail, which will let me recover something like the cohomology of this from the cohomologies where I replace V by these other valuation rings,
thank you.
which have smaller dimension. Okay, so in this way I run some induction on the dimension and I get down to the case of dimension 1.
So Robert has a question?
Did I get some sort of finite value of dimension boxes that this itself?
You didn't, but since everything inside mutual filter coordinates, I can begin by reducing to the case of finite.
Okay, thank you.
So next I claim that for any FP scheme X, there is a filtration on its mod P A1 invariant K theory with graded pieces given by these cohomologies that we're interested in, sitting in some appropriate degree. So why is that? So let me write up the catchphrase and I'll remind you. We know that to recover A1 invariant K theory from K theory, to recover A1 invariant K theory from K theory, the final A1 localization is not necessary. That's the point I made at the beginning of the talk. Okay, so suppose I ran my whole construction up to this point, but I dropped the final A1 localization. I would still get some filtration on KH. I just wouldn't know that the graded pieces were A1 invariant. And what would those graded pieces be? They would be precisely this without imposing A1 invariance. So I'm in this kind of weird situation. I've got my A1 invariant K theory equipped with some filtration, but I don't know that the graded pieces of this filtration are A1 invariant. That's what we're trying to prove. So let me now look at the difference. Let me now look at the filtration on the difference between the K theory of V and the K theory of V of point T. So I'm going to apply part 2 to both V and V adjoint T. and I get a filtration on that difference with graded pieces given by the difference between this construction on V and this construction on V of T. This is just functionality of filtrations. And what are those graded pieces? Those graded pieces are the cofibers of these matched EJs. Okay, again, sitting in some appropriate place. That's that clear. I'm just applying functionality in two to both V and V of T. Let me give this a name. Let me call it something like CJV. So now I have some filtered spectrum. I've got these graded pieces. And what I want you to know about these graded pieces is that they're not very big. Right? I'm looking at the cofiber of this. Now, V was a valuation ring of rank at most 1. Now, who remembers how valuative dimension behaves when I add a polynomial variable? It goes up by at most 1. It behaves right. It goes up by exactly 1. So V of T has valuative dimension 2. And we know that the valuative dimension provides a vanishing bound for cohomology, for CDH cohomology. So this thing has CDH cohomology going at most out to degree 2. And so this cofiber, this is just sitting in degrees 0, 1, and 2. And so how does the spectral sequence associated to this filtration look?
Sorry, what about you?
Yes.
If you're plugging KH, isn't that enough equal to whatever or you once distance or you even right?
Yeah. Yeah.
Just trying to prove it worked.
But not the K,
Yeah.
I see.
Okay, so how does my spectral sequence look? Right, I put together all the cohomologies of all the graded pieces. Sorry, that should be a C0 H2 C0 V 8 0 C1 of V H1 C1 of V H2 C1 of V. Okay, and then I get zeros by this valuative dimension argument. Right, there's no higher cohomology of these complexes. There's no negative cohomologies. Okay, everything up here is also 0. And my spectral sequence continues down here, right? I get all the cohomologies of all of these various CJVs. And what's this spectral sequence converging to? My punchline has already been ruined. Converging to the homotopic groups of this. So this is 0. Because it's A1 invariant K0. So the game is that I've got some spectral sequence, it's converging to 0, and the theorem to be proved is that all the terms in the spectral sequence are 0. And we can do this because sometimes spectral sequences are small. I mean, if it was a massive spectral sequence, I would stand no chance of deducing from the fact that the abutment was 0, that the E2 plate was 0. But now my spectral sequence is small enough that I stand some hope. So what can we say? Well, the column of H1s, this is already stable. There's no differentials in or out. So if I'm converging to 0, this column of H1 has already got to be 0. Now, in practice, I don't know how to argue directly from this spectral sequence. What one should do is run the same spectral sequence, and instead of working with motivic cohomology mod P, you should work with the P completion of motivic cohomology. But then some very similar argument goes through. I mean, this is the mod P argument, but the same thing works modulo any power of P. You take the limit, and you get some similar spectral sequence, but with P completed coefficients. And the H0 column of the, let's say, P complete analog of the spectral sequence is torsion free. Because it's essentially some H0s of some P complete sheaves. An H0 of, sorry, some H0 of some P torsion free sheaf. And for each of the sections, then the global sections, that also be torsion free. But that spectral sequence, again, the one for the P completed cohomology, degenerates rationally. This is a standard argument in kinetic cohomology and characteristic P. You have the Frobenius, x goes to x to the P, acting on everything inside. And because it acts on everything inside, all the spectral sequences are compatible with it. But how does the Frobenius act on an omega J? This is generated by things that look like df1 over f1, where some dfj to fj. And if I replace f by f to the p, it multiplies df over f by p. So if I have j subforms, it multiplies it by p to the j. So I have the Frobenius acting everywhere on this spectral sequence, and on the jth row, it acts as multiplication by p to the j. But the differentials are compatible with it. And if you have a map which is compatible with multiplication by p to the j minus 1 on the source and p to the j on the target, then it's got to be a torsion differential. It's got to produce torsion element and a torsion kernel killed by p to the j minus p to the j minus 1. So we've just said that the H0 line is torsion free. So they're torsion free. So the kernels of the differentials have got to be both torsion and torsion free. So all differentials are zero. That was in the mechanic version of the spectral sequence, but you can go mod P and get the result from the mod P spectral sequence. And so you deduce that all of these CJVs are zero in J. And that completes the proof. So we've proved something about motivic cohomology using what we already know on the K-theory side. And it's the same style of argument that's used to prove projective bundle formula like time and time again throughout the theory. We don't know any way to prove it directly to the cohomology theory itself, but we find some way to extract the information from what we know about K-theory or some other localizing event.
Sorry. So in the last few lectures, I just don't recall right now, we talked about the filtration of KH being exhaustive but not complete or something.
Okay, right. So I didn't make a big deal about that. Indeed, so I'll be complete as soon as my scheme has finite value to dimension.
And we use this here too.
That's being implicitly used here. That's being implicitly used. And in general, if you want to make such a it's now disappeared. If you want to prove such a theorem, you can also take some filtered colimit at the very beginning to reduce the case of the scheme that even the theorem and they're finite. So in a theory, even a finite type over FP, and then again, a finite value to dimension, the filtration will be complete.
So technique question. So in the first step, could you please rephrase this reduction in terms of something like arc defect?
CDR. The things are not arc sheaves because arc sheaves are tau sheaves, but there's a completely decomposed variant of the arc topology of Manto, Oiwa, Iwasa, and Kelly, which is in fact what I should be cycling to this excision argument, and which indeed uses techniques from the CDR topology. Yes. I think that's all I want to say about the A1 invariant theory. If there's no question, I'll finish with half an hour left. I can say something about the non-A1 invariant. Thanks. Right, so as I said, so this style of argument is used to prove projective bundle formula in the A1 invariant theory, also in the non-A1 invariant theory. This is probably the simplest case of it, because really the spectral sequence is very small. If you want to prove projective bundle formula with mod L coefficients away from the characteristic, it's maybe a similar degree of complexity. And then the worst case is when you want to prove it with mod P coefficients in mixed characteristic. When you have some mixed characteristic 0P, then you've really got all of the symptomic homology, it spreads out a lot more. And you understand projective bundle formula for some bits of it, but not for some other bits. And so you try to govern the other bits using some localizing invariant that you cook up and build some spectral point. And it gets messier and messier. But it's always this idea that we try to extract as much information as we can from non-commutative invariants. Even though we only want to prove things about cohomology.
There was also, I mean, the symptomic homology part, but there's also a LA1 that was sitting outside, right?
But that's what we just killed. It is mod P and characteristic P, that's what we just killed. We just proved that this A1 was not necessary.
Then only you go and try to prove the projective bundle formula.
Yeah. Well, like, in fact, right, that's the order of logic. Indeed. Once you kill the LA1, now you're just trying to prove projective bundle formula. Yeah, good point. So what's left? If I'm working mod P and characteristic P, what's left to prove projective bundle formula? Since I've killed the LA1, I now just need to prove it for these. There's no longer an LA1. But now I want the same argument. Because KH satisfies projective bundle formula. So I look at a spectral sequence measuring the failure of this to satisfy projective bundle formula. It's again going to be a very small spectral sequence. And I'll extract projective bundle formula for that from the fact that it wasn't KH. Maybe no one was there. But so the final goal of these talks was to define to you some non-A1 invariant motivic cohomology theory for general schemes. And for simplicity, as I've in fact already done so far today, I'm going to restrict attention to schemes of characteristics. It will already illustrate some of the main ideas. So this is already appeared in one of the discussion sessions, but let me write it down again. I mentioned this dichotomy in the second talk, that somehow everything should be built from A1 invariant stuff and stuff which is very far from being A1 invariant, like differential forms. And besides all of that dichotomy is the following theorem. In its modern formulation to be attributed to Kirchner-Tanner and Lantana. But in characteristic 0, okay, we should be on board. In characteristic 0 goes back to Cortinius, Hessenmeyer, Schlichting, and Weigel. And it says that if I look at the difference between K theory and topological cyclic homology via the trace map, then this difference is a CDH sheet. So in other words, for any scheme X, if I look at the K theory of X, topological cyclic homology of X, and then I CDH simplify, then this square is Cartesian. But we know that the CDH simplification of K theory is A1 invariant K theory. We can add that in. So in other words, we can recover the K theory of X from A1 invariant K theory of X. Let me say, and topological cyclic homology. Not only topological cyclic homology of X, but also topological cyclic homology information coming from blow-ups of X. And the idea is we're going to do the same to define motivic homology. So here goes the non A1 invariant, if you like. In fact, I prefer to say A1 invariant motivic homology and motivic homology rather than motivic homology and non A1 invariant motivic homology. By preference, it should not necessarily be A1 invariant.
Be A1 dependent.
But
Could be A1 dependent.
A1 dependent, that's a.
Be A1 it's very.
I also don't like this because it suggests that it's always non A1 invariant. It should be not necessarily A1 invariant.
Yes.
It gets a bit long. Yeah, actually, A1 dependent is it kind of sound like a joke bomb. It doesn't let us dating A1 to start the stuff. Okay, the A1 invariant motivic homology of any FP scheme X is defined to the following pullback square. So down at the bottom left, I put the A1 invariant motivic homology of X. Up at the top right, I put the symptomic homology of X. And I glue them along the CDH simplification of the symptomic homology of X. So CDH simplification of the symptomic homology cause of X. Let me remind you that here on TC, we have a filtration with gradients given by symptomic cohomology. And since that's not taller than X, I can just CDH cheapify it as well. And we see that the CDH cheapification of the topological cyclic homology will carry a filtration with gradients given by the CDH cheapified symptomic cohomology. Okay, again, there's my usual favorite tip. And meanwhile, down A1 invariant K theory, we know that we have our motivic filtration with gradients given by A1 invariant motivic cohomology. And so I glue together these pieces in the same way as K theory is glued together from the corresponding non-commuting invariants.
This is where you need to be an FP scheme because otherwise you would not know what to.
This statement that the topological cyclic homology carries a filtration with these gradients is only true when I. Okay, it depends exactly what I mean by topological homology. Okay. The statement that the topological cyclic homology of a ring has a filtration with these gradients is only true when the ring is P complete. So if I'm in terms of P, I'm good. I want to be able to CDH cheapify. I can't really CDH cheapify while restricting to P complete things. Because if I blow up something P complete, it's no longer going to be P complete. So the particular recipe as I've written down here works in characteristic P. Okay. If I go in characteristic 0, then I have an analogous statement as this square. I mean, indeed, really, this theorem is not restricted to characteristic P. There's this theorem that there's holds for any scheme. And what I would have to put at the top right would then be the full integral form of topological cyclic homology. So, for example, on schemes over Q, that would be negative cyclic homology. Negative cyclic homology carries a filtration with gradients given by pieces of derived Durand cohomology. And I would carry out the same construction, but symptomic cohomology would turn into pieces of Hodgkin pieces of derived Durand cohomology. And if you're a mixed characteristic, then you somehow have to glue in pieces both coming from symptomic cohomology and from derived Durand cohomology, but motivated on the same type of construction. So it's the simplicity of the definition that I restrict to FP schemes, but there's a similar recipe that holds what any scheme. But
Fantastic.
okay.
Fantastic.
Wait, sorry, I didn't quite understand. How are you dealing with the Archimedean places for other?
Oh, an FP scheme.
Oh, sorry. I got excited.
Okay, what can I say about this? Okay, remark. It's not good to define things when you haven't defined the maps. Right? I said this top left is going to pull back these other pieces. So this is just the CDH cheapification map. But what's this map at the bottom? Let me give it to you mod P. To show you where there's a site sample P. I have my A1 invariant motivic cohomology mod P, which we know in general is given by this recipe. By the previous theorem, we know that in this case of FP schemes, I can drop the A1 localization. And now I can drop the truncation. And if I drop the truncation, then I map to the symptomic cohomology, again, I don't think mod P for simplicity. But that's defined from the map appearing here. Mod P. And it was crucial to have that previous theorem that I could drop the A1 localization, because otherwise I've ended up in the A1 localization of the CDH simplification of symptomic cohomology, which is 0. So I would not have managed to do any interesting construction. So this elimination of the A1 simplification is somehow not just useful, but it's crucial for the construction of the non-A1 invariant theory.
That was actually the point I was worried about, how you did that in general.
That particular map in general.
Yeah,
Okay. So in characteristic 0, the same thing works. You can eliminate the A1 localization, and you can construct a map.
okay, so that works, so you can eliminate the A1 localization.
So over fields, you can eliminate it in general. In mixed characteristic, this is unknown. And so then what you do is in fact, you don't put this theory at the bottom left of the diagram. You put the theory without the A1 localization. So you don't know that the bottom left of your diagram is A1 invariant, but it turns out that you don't care. Turns out you can carry out the construction and prove all the terms that you want. This is what Test Luis has done, without knowing whether the bottom left of the diagram is A1 invariant. You can bypass the bottom of the
Sorry, you also said that the A1 localization of the CDH of the symptomic thing was 0?
Yeah, I'll come back to this in a second. Yeah.
Yeah, but is this also true if you don't CDH?
Yes.
slightly?
Yes. Yeah, I'll say something about this in a second. In fact. So the second point is that, okay, someone has stopped numbering this is the theorem, this is not that theorem. Okay, yeah, I do understand what we've done. This is the A1 invariance theorem from earlier. Provided the previous theorem, or by this square plus design, we get the filtration on K by X. With gradients given by these motivic cohomologies. In fact, what one is really saying is I already have filtration here, filtration here, filtration here. I know that if I forget the filtration, then this is the pullback of those terms. And I say, let's just carry out this pullback construction in filtered spectrum instead. So it upgrades K theory to have the structure of a filtered spectrum whose graded pieces are precisely these things that I've written down. So by construction, I get my desired Tier Hertzberg filtration on the K theory of my arbitrary FP scheme. And so I get my desired Tier Hertzberg spectral sequence. Converging now to be honest, not necessarily A1 invariant K theory of my scheme, and everything inside splits rationally. And in this case, this is easy to prove because I have my Frobenius. I can carry out the same argument that we did with the spectral sequence a moment ago. Frobenius acts functorially on everything inside, and in particular, it will act on the weight J motivic complex as multiplication by P to the J. And so the differentials occurring in this spectral sequence are forced to all have torsion kernel programs. And so rationally everything degenerates, and my K theory will just decompose into some of my homology.
I have a question.
Yes.
Sorry if I missed this, but so modding out by P is sort of like modding out by the Frobenius, by applying Frobenius once, right? Okay, either way, how do you get, I didn't quite understand how you got from constructing a map mod P.
Okay, so then I do the same thing mod all powers of P. And then I take limit.
Okay, and then
it's basically just that. Yeah. So I went mod P for simplicity, but it's basically I do mod all powers of P and then I take limit.
Yeah.
Because I'm more or less, it's not quite true. This thing's basically people proof. That's actually a slight lie, but you might as well pretend that's true.
Ah, okay, okay.
So I just constructed model without it. Okay, let me now answer a question that was asked about imposing A1 invariance in symptomatic cohomology. Let me start with imposing CDH cheapiness. Okay, symptomatic cohomology will drastically fail to be a CDH cheap. So otherwise, this right arrow would not be interesting. And so the motivic cohomology is also failing to be a CDH cheap. I mean, it's got to be because K theory is not a CDH cheap. What happens if I force it to be a CDH cheap? Well, if I apply CDH cheapification everywhere in the diagram, the arrow on the right becomes an equivalent by definition. And therefore, so does the arrow on the left. So if I force my motivic cohomology to be a CDH cheap, I recover the older A1 invariant theory. In the same way as if I force K theory to be a CDH sheaf, I recover KH. It's a motivic upgrade of that statement. Okay, but how was KH originally defined? It was defined by A1 localizing K theory. But what if I do the same here? What if I A1 localize the non-A1 invariant motivic cohomology? I tell you, it'll kill the things on the right. Because the things on the right ultimately built out of like cotangent complex and differential forms, and we had this observation back in the second lecture that these are far from being homotopy invariant. They're killed when I impose A1 invariance. So if I impose A1 invariance everywhere, it turns the non-A1 invariant theory into the A1 invariant set. So that's why I sometimes like to say that this motivic cohomology is it's a CDH de-sheafification of the A1 invariant theory, or an A1 delocalization of it. It undoes the excessively strong structure that the A1 invariant theory has, but we can nevertheless recover it. I think I already made the comment that things like projective bundle formula hold by applying the sometimes spectral sequences of small argument. And what else can I say? So I would make some comments about more general case than FP schemes. If you plug in Q schemes, you repeat some construction with derived Durand cohomology. If you plug in mixed characteristic schemes, then you have to take care of both the symptomatic cohomology and the derived Durand cohomology and carefully glue them all together. And we run a similar recipe. I stated more properties of the theorem way back in theorem 1.3 in the first talk. So we have the expected relation to minimal K theory. We have all multiplicative structure that you want. We have Bayes and Lichtenbaum stylized models. So maybe I point that one out. Right. But maybe that's particularly interesting in light of what we saw earlier today in the discussion session. So what happens if I take my motivic cohomology mod L, for some L which is not equal to P? Anyone? I just get the A1 theory. These are p-adic cohomology theorems. L is invertible in them. When I go mod L, they disappear. And so when I go mod L, I just recover the A1 invariant theory. As I should, because on FP schemes, A theory mod L is the same as A1 invariant K theory. I'm saying the equivalence also holds at the level of motivic cohomology. And so now I leave you with an exercise. We do the calculation from the discussion session and compute the mod P motivic cohomology of this surface. Right, so this morning I calculated for you mod L, but I calculated for you a whole bunch of motivic A1 invariant motivic cohomology, including mod L of some simple surface. And now the interesting extra data, there's no interesting extra mod L data in the new theory. The interesting information is all p-adic. But you can go away and try to compute things like the symptomic cohomology and the CDH secret-like symptomic cohomology of a surface. And these are now very computable invariants. And you can glue it back into the A1 calculations we saw this morning and compute the motivic cohomology and the p-adic motivic cohomology of this surface and characteristic P, and then compute K groups of such a surface, at least in certain places. I think I'll finish that. Thank you.